So I'm Neelansh, and he's my friend Adil, and we are engineers from InVideo. And InVideo is a AI video creation platform which will let you create professional-looking videos by simply entering a single text prompt. So InVideo already contains the word video, and our work also revolves heavily around working with graphics, rendering, and performance-sensitive workloads. And I would be happy to announce as well that InVideo was awarded the best app for 2025 by Google Play. And yeah, so when we mention uh, what has motivated us to be here at Fluttercon. So while our journey at InVideo, uh, we have been working with products that are focused on rendering and require high performance and consistent control over GPU. And what we wanted also was a single code base that would run on all three different platforms. So per to say Android, iOS, and web as well. So Flutter out of the box didn't provide us with a lot of fine-grained control over when we have to work with graphics layer. So naturally, we led to exploring a native rendering engine. And in this journey, we also encountered a couple of problems. And so the first one being that Flutter doesn't provide us with a native rendering loop. So what does a native rendering loop help us with? It helps us gain control over the update and draw calls, and also provides us with the low-level APIs, which helps us directly work with GPU as well. So, and it also provides us control to pass our custom events if we have to, for example, work with a canvas which has a character, you want to move the character from left to right. So we would be taking this as an example through our slides as well, where we give a direction to, where we actually pass an event to the character to move from left direction to the right. Okay.
Okay. How Nilansh pointed that our problem was basically we wanted more control on the graphics layer so that we could draw more, control the loops, and have more control over how graphics is drawn on the screen. So unfortunately, Flutter does not provide us with a loop. So we had to come up with our own solution. And coming up with our own solution means we had to be smart. Why? Because we had to make sure that we wrote the engine once and it worked across multiple platforms. It had to work on iOS, it had to work on the web, it had to work on Android as well. So our solution basically was creating a native rendering engine, which we will go throughout the course of the slides. It has to seamlessly embed in Flutter. So Flutter has a very thoughtful rendering cycle, right? You have render object, it does all of the things. Our rendering engine should not disrupt this existing pipeline. It should work seamlessly. It should get hold of the graphics layer without interrupting anything else in the Flutter pipeline. Second thing is event driven. We need to give it a command and it has to execute that without any interruptions. Cross-platform support, like I said, it had to work seamlessly well at 60 FPS because a human eye requires a minimum of 24 FPS for something to look super smooth on screen. And we needed something that would work across all the platforms. And the last thing that you can see is we wrote it in Rust, and I'll elaborate why. Okay, so why Rust? So when it comes to writing low-level code, we have tons of options there, right? We have C, we have C++. Rust was one thing that we experimented on. So initially we started with C, we started with C++, and it had a lot of tedious things to do, right? You want to allocate memory, you have to deallocate memory, you have to be smart about it. So these are certain things that kind of were a turn off, frankly. Rust, on the other side, was a very smart language. It had amazing syntax. It worked great out of the box. And if Rust compiles, you can pretty much guarantee that the code will work. If you have logical errors, it can't help you in that, unfortunately, obviously. So one best thing that I like about Rust is the concurrency model that it has. Like you have multiple threads running all over the place, and suppose those threads are sharing some kind of resource, maybe some object or something that it wants to access. If two threads try to access at the same time, that's when a deadlock comes, right? Because one flow is waiting for the other one to release. Rust is very smart in these things. If your Rust code compiles, you can pretty much guarantee that this thing does not exist. There will be no deadlocks. There will be no two threads at any point of time accessing the same things. So why Rust? Performance at C, C++ level, if not Better than that, more or less to that. It didn't have a GC, so you have control over when to allocate things. Predictable, stable runtime. So this is what I meant by if the Rust code compiles, it pretty much guarantees that it will work. Excellent cross-platform. So Rust has this great targeting system, right? So for Rust, you use something called as Cargo. It has a great platform. You write the code only once, and give and take small tweaks for platforms. It will literally compile the code. So 90% of your code will probably be the same thing that you run across all the platforms, which is brilliant. Why? You are not maintaining multiple code bases. You just write the code once. If it compiles once, you ship. And shipping to the market should always be the goal. The faster you ship, the better you get results. Strong graphics ecosystem. So over the years, Rust has been improved so much. The community has been very generous. A lot of people have written a lot of crates. So when I say what are crates, right? Crates are basically your dependencies that we have in PubSpec. We call them crates in Rust. There are ample of crates which help you to access the graphics layer. Not only that, any other thing like any heavy computational task, there is always going to be a crate out there. Secondly, it works seamlessly with Flutter via Flutter Rust Bridge, which we'll speak about. Yeah. So going forward. Okay. So that's about Rust. Now let's come back to the whole ecosystem that we're trying to create. So this is our hierarchy. This is the whole architecture that we have built in NVIDIA, plus that we're going to demo over here today as well. So basically, if you see the topmost, we have Flutter, obviously, because that's what we are here for. Flutter interacts with something called as a platform view, which we'll speak about. The platform view, on the contrary, splits the code into the platform, right? Because it's platform view. Then you go to platform specific, which is your Android, iOS. Then it gives you a graphical context, and then the Rust engine comes right at the bottom. What you see at the bottom, the Rust rendering engine, that's the superpower. That's where actually all the logic of rendering comes. The layers above that are just orchestration to get to that layer. It is just a way for you to build your whole communication and a way for you to host the UI in the Flutter ecosystem. All right. So let's talk about the first part. So embedding a native renderer in Flutter, right? So how do we do this? Like I'm a guy, I open my Flutter project. I'm like, hey, you know what? I want to render a native view. Now this has nothing to do with graphics. It has nothing to do with the OpenGL layer. It has nothing to do with the GL. Just a normal view. Assume all of us would have used Android, iOS, Kotlin, Swift, whatever, right? And we have our so-called text views, which extend a normal view, or we have an image view, or we have, these are all specific to your platforms. What if I want my Flutter app, which is written in pure Dart, to host any of these views? It doesn't matter what it is. Like if it's written in Kotlin, you want to host it in your Flutter. So that's where the native surface comes in. So that's what a platform view is, right? A platform view is basically, you can think of it like a magical portal between your native Android code, iOS code, and your Flutter code. It just works seamlessly. You write your stuff in Kotlin, you render a view over there, and it magically comes in your Flutter app. And you don't have to do any excessive work for it. These two widgets are over there, which work brilliantly well right now. And this is all the setup you need to get any view from your Kotlin code, from your native code to render on Flutter. As simple as that. As you can see, there are two things. And as always, you have to write a lot of code for Android for some reason. iOS just works with 3-4 lines. Yeah, you guys know about that, right? Yeah. So yeah, so this is the code that you write on your on the Flutter side of things, on the Dart side of things. It is basically just a normal widget, like how you write any other widget. Now this is on the Dart side. And how does a native view, basically your platform, your main activity.kt, your Swift file, how does it know, okay, this view is something to be rendered over here, right? So how do we do that? Yeah. So in your KT files or your Swift files, or when you come on the native side of things, you create a factory, and if you see the create function in the factory at line number 8 over there, we return a view. Now this is the view that we have created for this demo purpose, but it can be anything. It can be a text view, it can be a linear layout, whatever you guys want, you can dump it over there and it will render on the screen. So basically this is just a very bare minimum setup of how to get a normal view from your native Android, iOS to your Flutter side or to your Dart side. Make sense so far, right? Okay, yeah. So that's all the easy things, right? That's the easy stuff. We just got a view on screen. Now we are coming to the actual magic. Now we go to the realms of graphics. Now we go to the realms of, hey, you know what? Let me use shaders. Let me use something on, let me draw something on the screen. Let me use the GPU of the system right now. This is where we come in. So like I said, Flutter does not provide any so-called widget, at least out of the box, wherein uh, you have access to this graphics. So you cannot just draw a graphics layer on any view. You need a view that gives you an OpenGL context. You need a view that gives you a context of the drivers on your system, right? So if you talk about Android, we have something that is called a GL renderer, right? A GL view, GL surface view. That's where our cameras work, our video players work, our Exo player works. Exo player has issues. So yeah. So if you talk about this, when it comes to Android, we will use something called as a GL surface view. When it comes to iOS, we will use something called like a GLK view. Pretty much the same thing. They both have GL. All right. Yeah. So basically, the whole goal is to get access of a rendering engine, right? To make a rendering engine of your own. Now, what is a rendering engine? Let's go back. Let's go back to basics. What is a rendering engine? Okay, all of us have seen movies, right? Have you seen the old school movies? They are nothing but a sequence of images stitched together, which just gets played really super fast so that your eyes get fooled that it looks like a sequence, which makes it move. That's what a movie is basically, right? So when I'm creating a renderer loop, what does it mean? It means you need a mechanism, you need a thread, you need something that ticks so fast that you provided images and those images look like a sequence. And that's how a video is made. That's how games are made, as a matter of fact. What is a game? Game is nothing but at 60 FPS, 24 FPS, whatever FPS you call it, right? Frames per second. You draw that many frames on the screen. You clear the screen, you draw. You clear the screen, you draw. You clear the screen, you draw. That's what happens. And it looks like a sequence of images. It looks like a video. So basically, this is what we were trying to achieve. We were trying to get a renderer loop. And the bare minimum things for a renderer loop is two things. You update the state. For example, you have a character that's moving from, say, point A to point B. If you don't move its XY coordinate, it's not going to move, right? So that's the update part. And then the draw part. So what does the draw do basically? Whatever state you have previously updated, it will just draw that on the screen. So if you see that image as well, the stick guy who's moving his hand, at each tick, you can think of each of that page as a tick, right? The coordinates of the arms are kind of moving, which looks like a sequence. So this is what we were trying to achieve. We were trying to get a hold of this. Okay. So how do we get that, right? So GL renderer. I'm pretty sure most of us have come across GL render somewhere in our life. Probably if you're using a camera, or probably if you thought of going deep dive in some player or creating some custom things on the graphics layer. So let me like quickly go through this, right? So what does this provide? So Flutter doesn't have any, doesn't offer any native render, like I said. So either you create a ticker of your own, which can be as good as a for loop also, but not the best. It can be a thread also, again, not the best probably. And something that also manages the device rotation, resizing, because when you have a rendered thing or canvas on the screen, the moment you rotate it, you are going to reallocate stuff, you are going to resize stuff. You cannot keep the character the same way, right? Then you're going to end up having a big small screen with a small character. You need to do all of the things. GL context loss. One of the most common problem that you will face in Android. iOS brilliantly takes care of it. For Android, some reason, depending on the OS, Samsung, whatever it is, they clear the context. All those things goes for a toss. So we need a mechanism that kind of helps us orchestrate all this behavior and gives us this control. So if you see the GL render, right, that we have, it has three main functions basically. Ignore the destroy function, that's what we have written. But what it provides out of the box is a surface created. That is basically when the surface, the OpenGL surface, has been created on the screen. That means your GL context, you are ready to use your graphics layer right now. Then the surface change, obviously you rotate your device, blah blah blah. It needs to, it calls that wherein you reconfigure stuff, get things working again. And then it has a on draw frame. So this on draw frame is the only function that gets called n number of times, right? It just keeps getting called. If you just put a logger over there, you can see it get called all the times. And that's the whole purpose of it, because that is your render loop. That is the one that will actually allow you to update the state on each stick and draw. Now, depending on how good your system is, by system I mean your mobile, your devices, that many times it will take. Most probably 24 being the minimum, 30 being the minimum, it will work, which is good enough for movies. If you're going all the way to games, 60 is what they recommend. So that's why you say, okay, hey, you know what, this game for some reason looks very laggy on my phone. Most probably it's a low-end phone that doesn't have that much good of a rendering power. It doesn't take that good, so it looks like it's lagging, right? But if you go to a high-end phones, you go to your Samsungs, you go to your Pixels, probably you will not see those things in the very same game that are playing on the other phones, right? because they tick that good. Their GPUs are that brilliant. All right, makes sense so far? Yeah, amazing. Okay, so now comes the fun part, right? So we already spoke about why we went for Rust. Let me talk about what is the Rust rendering engine now. So let's not mistaken one thing. Rust is not only required for rendering stuff, right? You can do anything, any computational task that is very heavy. You can write it in Rust and you can use it via this same orchestration more or less. Give Keep aside the GL renderer because obviously that's for graphics. Suppose you have some really heavy image processing that you want to do, and it is blocking your thread. It is lagging. You can probably outsource this thing to your create a small package in Rust and use that whole orchestration over here. Things will work fine. And that same thing, then you can pass it on to iOS, you can pass it on to web and give and take few tweaks. The same thing comes over there. So yeah. So in our example, right? In our example, what's the role of Rust? What is our Rust engine that we call currently doing? So you can see there are three main functions, right? We initialize the game, we update the game, we render the game. Like I told you, update and render is very important. Update is the thing that updates the state of your game, your character, your whatever your application that is. And render is the thing that draws that updated state on the screen. And the init function is obviously an initialization function that gets called only once, which you choose on your benefit, which is the best part of which time for you to call. For us, calling the game init makes more sense in the surface created part that I showed over there, because that is one thing that gets called only once and you initialize this entire thing just once. And then you do the update and render, right? So how do we initialize? Next thing is how do we initialize this thing, right? Uh, I think so. It does, let's just focus upon what these functions basically do rather than going into nitty-gritties of these functions, right? So when it comes to graphics, especially iOS is brilliant because they use the same hardware, they use the same OS, the same backend across all phones, right? Because that's how they are. That's how their ecosystem is. So when it comes to iOS, you can see those fancy little lines over there written on top, something called as target underscore OS iOS, and there is target underscore Android. So basically, it means that when you compile your code, when you compile with whatever command that Rust provides, you mention the target. The one, if you give the target as Android, it will only include that code. The one in iOS is not included at all. Now, similarly, if this target code is dependent on another target code, it will only compile that. It will only include that in your binary, right? So, in short, I will tell you what these functions do. Not going too in depth in it. These functions basically interact with your GPU and finds where the GL functions are. So basically, you have GL clear. You have a lot of graphics functions. They are actually loaded in your GPU, and these things actually help in getting the pointers, the address, right? It takes it, it makes a list of it, and then whenever you want, you can use it. So this is basically what they do. Okay, so this is the update state. Again, as you can see, there is a keyword over there called pub external, right? EXTRN. So what does that basically do? It basically says that this function is something that will be accessed outside the realms of Rust. Anybody who is outside, it can be web, it can be a JS, it can be anyone who wants to access this code, you need to specify this external over here. And as you can see, it is game set direction. Like I think so. I hope it is self-explanatory. It basically changes the direction of whatever thing is being rendered on the screen. So as you can see, it takes in the current state, which is the handler in that case, and you can see that at line number 9, we're taking the state and we're updating the direction. So this is what I mean by updating the state. Whenever you tick, you update the state and let the next thing get rendered on screen. Does it make sense? So there is something, if you can see, there is a fancy line on top at line number 2 called no mangle, right? So since you are working between two realms, like this is going to be interacted by the world outside Rust, for example, Kotlin or Swift. They will not, if you remove that no mangle and you run your code, that game underscore set will become gibberish. It will not make sense, which means anybody from the external will not understand. This is as good as a ProGuard, like how things become gibberish when you run things. Then when it can't be found, we put a rule right in ProGuard. Hey, you know what? Keep this fellow the way it is. So this is basically no mangle. So you basically say don't change this so that the Java code, the Kotlin code, the Swift code can easily find these functions. Okay. And this is the render. This is the third part that I was talking about. As you can see, we are using some fancy tools over there called egui. Not necessary to understand. Basically, this is just drawing an object on the screen. This is just an example. We remove the meaning out of it. Don't look at the code. In short, what we are doing is that this game render is going to get called at 60 FPS or however whatever FPS, like I said, and whatever is the current state, as you can see over there, it will just draw that state on screen. Cool.
So I guess Adil has thrown a couple of complexity at you guys. So let's do a quick recap. What we have talked as of now is that we have three different layers. First is our Flutter or the Dart side of things having platform views. Then on the native side, we have our GL renderer for both Android and iOS. And then we have some Rust implementations in our engine. So what are we actually missing? So yes, communication is the key. So all these layers won't matter if there is like no communication between these layers. And for that, we would be talking about how to communicate between our Flutter and the GL renderer part, and then GL renderer talking to our Rust code, and some Dart to Rust interop as well. So starting with, I think this is very simple, and most of you have always been using method channels whenever you are integrating a plugin into your app. So this is our since our GL renderer is a platform code written in Android using Kotlin and in Swift using iOS. So we would simply create a method channel. Method channel is basically a way provided by Flutter for us to call native platform code. So we create, we are being, in this example, you can see using the same example of a character, we are trying to move from left to right. So you can see we have a function called as send direction, which we can call, which you can call with the required argument and pass that direction. And this would be talking to our GL renderer, which is written on the native side. Okay, now comes the fun part. So how our GL renderer is going to talk to the Rust code. So in Rust, we have seen we have a game state which consists of like what is the position of my character, the X and Y coordinates, in which direction the character is moving. But we don't have the implementation of that in our Kotlin code. So for this, we would be using something called as JNI. JNI is a Java native interface. It is basically a programmable framework where it allows Java to run inside JVM environments to interoperate with other libraries written in C, C++, or Rust. So a simple JNI function here you can see is we define by providing the package name and concatenating it with the function which we are trying to call, which is written which is written in the Rust code. So here you can see com example flutter con is my package name and it is concatenated with the native send direction set direction function. So we can pass that direction as an argument, we can define enums and do all these things. But how does my GL renderer class know that how would the function definition look like? So for that, we would have to write a simple, I could say, methods which are just like a blueprint of how my function would behave inside the Rust code. So if you see inside the game native class, the screenshot here, you would see that this already has a function called as set direction at line number 13, and similarly other functions like render, update, to resize and even initialize. So how does this work on the Android side is basically we are using something called as dynamic linking. Dynamic linking is like you have to integrate the library at runtime instead of compile time. So our Rust code has the implementation of this function called as set direction, and we compile that code which gives us a shared object, and we copy that shared object in our JNI libs folder based on the architecture. And whenever this code compiles, at runtime, the game engine library is loaded, and whenever the set direction function is called from the Flutter side, it goes to the GL renderer, and GL renderer calls the Rust code. So this is how how things are orchestrated on the Android side. And this is an example of how GL renderer is going to call other functions. So Adil has already been talked about how on surface changed, on draw frame, and all these things are already provided by the GL renderer class, and we can call the game set direction function, game update, game render accordingly. Okay, now let's talk about how things are done on the iOS side. So in iOS, we would be using static linking instead of dynamic linking. Static linking is like you have to, you already have the compiled code, which gives you a .a file. You have to just copy paste the file inside your runner folder and give a blueprint or in a header file. For example, in this case, you can see game set direction. We are just defining a blueprint similarly to what we have been doing for Android as well. In the game native class, here we have a header file which has game set direction, game in it, and already the implementation has been coded into the .a files. So whenever we run the Flutter app, Flutter calls the native code, and native code already has that implementation from .a file. Okay, next.
So Neelansh was talking about the whole communication structure. So in this entire process of using a method channel to talk to your native view, the native view calls something inside your GL renderer, the GL renderer calls something inside your Rust code, right? So if you can see, this is a huge pipeline, which means you have to maintain it a lot, which means the rate of getting errors also is a lot, right? Because they are literally jumping through multiple ecosystems, which means if any of the ecosystems between them have a wrong type that is being returned or has a wrong signature of function, it will break. So we stumbled upon this really cool thing. It's called Flutter Rust Bridge. So what is Flutter Rust Bridge, right? It is like the name says, it's a bridge between Flutter and Rust. Basically, you write your code in Rust however you want to. You write the signature, you write whatever. And then the moment you run a command, which it provides over there, it will automatically create another Flutter or a Dart code, which is nothing but code calling the Rust file. And it is as simple as just making a function call. So this is one thing that is brilliant, because you don't have to do the whole thing of communicating between Dart, then go to Android or iOS, then go to a renderer, and then from a renderer go to a Rust. You are pretty much bypassing the entire thing and just going from Rust Dart all the way to your to your Rust. So if you see what it does, it bridges the gap between Dart and Rust. You can write code in Rust and call it like any other function. It is type safe. As a matter of fact, like the library is so matured that whatever typings you write in Rust, like if you're saying you're returning int or something like that, it is smart enough in Dart to know what would be the counterpart of it in Dart. It has async, so basically you can return futures and streams as well. And yeah, cross-platform, it works on, it helps in working with Android, iOS. So like I said before, it was a manual FFI, wherein you had to go from Dart to your method channel, to your Kotlin, Swift, JNI, and so called. So multiple layers. After that, you bypass everything, and things are actually less error prone. So your communication works really seamless. As a matter of fact, it even reduces latency because you're not jumping between multiple layers and async calls, right? So this is just a very small basic example of how it will look. If you write your code in Rust, say set direction I32, whatever it is, and then when you run the code or when you run the generator, you see it will return something. That it will return something as set direction. All you have to do is just call this in a Rust code, and whatever is or in your Flutter code, and whatever is there in the Rust just comes all the way back over here. Life gets very very easy. So yeah, I'll show you a small demo of of something that we made. It's highly inspired with what we do in InVideo of creating a rendering engine, but not as complex as that because that's way, way complex. Uh, Let me see if I have it open. No. Okay. So, uh, so you guys remember this DVD screensaver wallpaper that used to come on the screen in the olden times, right? So what do you see in the thing that's in black in the center? It is actually the Rust engine. It's hosted using a native view. It's hosted using a platform view, whatever we describe right now. And also, it is uh, the whole communication system is via the same thing that we said now, method channels that jump between multiple layers. So if you can see, the black thing is the only thing that is generated in the Rust and added. Everything else, the buttons, the FPS, and the buttons at the bottom, the keypad, those are everything pure Rust written. Yeah, pure Dart. Sorry, my bad. I'm jumping between multiple things. So yeah, so if you see this thing, if I just go into auto mode, this is basically what I was saying, right? The on drop frame right now is getting ticked heavily, and it is basically one image at a time being drawn on the screen, but it is happening so fast it looks like a sequence, and this is how a video is basically made. This is basically a low level way of defining how a video is made, the sequence of images put together, right? And then I was even talking about FPS, right? What happens if you have less FPS? Like for some reason your GPUs can't render that fast, right? So the moment you reduce your FPS, this is what happens. You start lagging. This is why games lag, right? Because you can't perform that well. So this starts lagging over there. See, it moves, and then the moment I go back to one, well, yeah, you guys can see that. So this is how we control the FPS. We needed all this control. We wanted to have fine-grained control on all these things to understand when to render things, when to control the time, when to control the loop. So we had to go down to native code. Yeah, and if you look at the manual thing, so this is basically orchestrating of how a command is passed from Dart all the way to Rust. So if I click on this, it has basically passed a command and it is going all the way over there. So this kind of demonstrates the whole orchestration of communication as well, or the whole orchestration of how we render a native view inside your Flutter app. So yeah.
Yeah. And cherry on the cake would be that even the assets that we are rendering here, these are interactive because each frame we register what are the touch events,
Yes.
and the touch events are then being passed to the game engine.
Yes. So basically, all the views have a touch event, right? That we get in Android. We just take the XY coordinates, we pass it all the way to Rust. We tell him, hey, you know what, this is our new X and Y coordinate, and it works. So it gives you a very it gives you a feel like it is being drawn on Rust and Flutter, but no, uh, it's there. So yeah, that's about it. And
That's right.
slideshow. Just one more slide, which is very important. Yeah,
Yeah.
there you go. I hope you guys enjoyed this. I hope it made sense first.
Yes. If you'd like to check the source code, that is available on the link here.
Yeah,
You
so I
can
have the
check out the
source
source
code over
code.
there. It has
Yeah.
the whole build, the build script. It has everything. It has everything from A to Z to get you started with making Rust work with Flutter, including the build scripts, including the whole orchestration. You guys can check it out. It's really cool.